Okay, it looks like we've got, I'll try to keep admitting some people here, but it looks like we're getting most people are in from the waiting room. So let's go ahead and get started. So I just want to say hello and welcome you to our first Ask Echometer online training session. It's great to see all your faces out there. So I'm going to give another little wave to all you guys. All right. So we've got people zooming in from all over the world, and we really appreciate you all taking the time to join us. My name is Carrie Ann Taylor, and along with myself from Echometer, we have Gustavo Fernandez, who joined us in December. Also Dr. Tony Podio, Dieter Becker, Ken Skinner, and of course, Lynn Rowland, who will be presenting today. As you may have noticed, your microphone was automatically muted when you entered the meeting room. So you can choose whether or not your camera is on, and we hope you'll keep it on because we love being able to see your faces. But we do want these sessions to be as interactive as possible. So we welcome questions from you. We're going to attempt to answer all of your questions during the allotted time. So we've opened up the chat to start accepting questions by text entry right away. So if you don't know where to access the chat, you should see the chat icon down at the bottom of your screen. So when you click that, you'll see the chat window pop up. And so there you can write your question or comment. You can see the questions and comments from the other participants too. So if we see a question that can be answered quickly, it will be answered in the chat. But if we see a question that might need some more explanation or one that would benefit everyone to hear, it will be directed to Lynn to answer during the Q&A session. So any remaining questions that have not been addressed by the end of the training session, we're going to answer in a follow-up email, and we'll send it out to everyone who's registered. So we'd like to attempt a few in-person questions during the Q&A. So if you're interested in asking a question to Lynn in person, go ahead and type your question in the chat, and then let us know you'd like to ask it in person. We're going to do our best to accommodate that because we'd love to hear some voices today. So we decided to call these weekly sessions Ask Echometer because we wanted to hear from you what topics you would like to see some training on. And we want to make it interactive so you can ask us the questions that you need answered. So this week's training session is on fluid levels. Next week's session is going to be on dynamometer analysis. And we've got sessions coming up on plunger lift, gas lift, bottom hole pressures, static bottom hole pressures. So we want to continue to hear from you what sessions you'd like for us to prepare for you. So ask Echometer, and we're going to respond with a session with some kind of a training for you guys. All right, so today's session is titled Direction of Kick on an Acoustic Trace. And it's going to cover interpreting an acoustic trace, understanding the direction of kick, finding holes in tubing, and then some different analysis methods for determining an accurate distance to the liquid level. And it's going to be presented by Lynn Rowland. So just to introduce Lynn, during his 40 years in the oil and gas industry, Lynn has received several awards for his work. He's authored more than 80 research and technical papers, co-authored a book on gas well deliquification, and holds a patent on plunger lift analysis. He's given hundreds of seminars and talks on efficient operation, optimization, and troubleshooting oil and gas wells. And we're so glad he's presenting today. So Lynn, I'll go ahead and turn it over to you now.
Well, thank you, Carrie Ann. Good morning, or I guess it's actually afternoon. This topic we're going to talk about came about because the oil industry started drilling in quite a few wells with liners and horizontal wells. And we started seeing these, frequently we'd see echoes at the top of the liner. We'd seen other conditions like holes and different types of echoes on acoustic traces, but the liners kind of drove the idea of the presentation. Plus in the new TAM software, we added a method that's called the downhole marker method, where the Wellbore overlay, Wellbore schematic, can be seen. And the Wellbore schematic typically identifies anomalies or objects in the well that increase the cross-sectional area or decrease the cross-sectional area. And those anomalies will show up as increases in upkick and a decrease in the wellbore as a downkick. I'd like to thank Carrie Ann and Gustavo Fernandez for help on this presentation. This new technology and the TAM software that that shows both the Wellbore diagram and the acoustic trace together, makes the distance to the liquid level easier to identify and also more accurately distance, because you can pick a downhole marker that's close to the liquid level. This also gives us a very good troubleshooting tool, where echoes that don't belong to the well and aren't the liquid level represent typically some kind of problem we may need to troubleshoot on the well. And so we're going to use this throughout this presentation, the direction of kick from an anomaly, whether it goes up or down, to identify how the overlay of the wellbore schematic matches with an echo on the wellbore. This downhole marker method has been available for a long time, but with the newest TAM software, we have added features where you can see multiple echoes from anomalies on the tubing and the casing that are supposed to be there, and it helps identify which kick is the liquid level. This is a valuable tool that helps us analyze and troubleshoot all kinds of different wells. Now, this is a definitions page that talks about what an acoustic fluid level is. And so here's your wellbore over on the right side, and this little circle represents the gas gun, and suddenly the volume chamber from the gas gun is opened, creating a sudden change in pressure, and that pressure change creates energy. When we say bang, the shot would be fired, and that sends this pressure wave down the well at the speed of sound. Well, the speed of sound, when someone says speed of sound, we often say the acoustic velocity. So when someone says speed of sound, or they say acoustic velocity, that typically means the same thing. Now, so this release of pressure is traveling, so we call it a traveling wave, and it travels through the gas, and it echoes typically off of any change in cross-sectional area. And so we show an echo off a collar, the collars, and we show echo off the perfs over here, and those echoes are up because the perfs are an increase in cross-sectional area, and then a big echo off the liquid level. So the size of the echo depends on the amplitude of the side, the height. It depends on the size of the obstruction. The bigger the obstruction, the bigger the echo. And so typically, not always, but typically the fluid level is the biggest obstruction. So normally you see the biggest down kick would be the liquid level, but not always. And so here on the acoustic trace, we see the collars or down kicks. We see an up kick from perf, up kick from another perf, up kick from another perf, and you can see the mark on the Wellbore schematic here of the perfs. And then you can see the down kick of the liquid level at the pump. And so if you didn't see the liquid level clearly, you would increase your differential pressure between the gun and the well, and that increase in pressure would make a bigger echo, a bigger amplitude, bigger height of kick. Now, this is again trying to show the concept of an echometer fluid level shot, and bang, the shot goes off. We send this traveling wave down the well, and at each of these changes in cross-sectional area, we get a reflection or an echo back to the microphone. And the biggest kick will be the shot going off, and then we'll get these smaller kicks from the collars, and then we'll get a fairly large echo, a big echo kick from the liquid level. And so if you have the pressure in the gas gun higher than the pressure in the well, then you would create what we call a compression pulse or explosion pulse. And then if you have the pressure in the gas gun less than the well, then we would create an implosion pulse. Now these pulses are acoustic traces. The pulses create acoustic traces, and the acoustic traces look exactly the same whether you do an implosion pulse or an explosion pulse on the kicks of the echoes. But when you do an implosion pulse, you drop the pressure at the surface to create the shot, whereas the explosion pulse or compression pulse, you increase the pressure. And so typically the kicks are, the implosion pulse would be upside down, and we have to tell the software that we did an implosion pulse, and then the software automatically turns the implosion pulse 180 degrees upside down so that the direction of kicks are exactly the same. Now this is a well, a gas storage well near Pittsburgh, Pennsylvania, and we've done a class on the gas storage well on how to analyze fluid level shots. And we talked about implosion shots and explosion shots, and so typically in a gas storage field, your casing pressure, tubing pressure would be high, and you would often do an implosion pulse. So one of the wells we went to had a casing pressure of 200 psi, and to create the shot, we did an implosion shot, and that's this shot right here, and we marked the software so it was implosion, so the lick level kicks down, and that's what happens when you check an implosion. We also said, we can add another 200 psi of pressure above the well pressure and make an explosion shot, and the shots will look exactly the same. And so you can see that the round trip travel time for the explosion shot is 2.505 seconds. The software determines the round trip travel time to the lick level echo to the nearest 1,000th of a second. And so these two shots are within 2/1000th of a second, and we could have fine-tuned them a little bit, made them exactly the same, but I'm showing that you don't have to make them exactly the same. These may be the initially automatically selected distance to the lick level by the software. So when you look at this, you can see that this trace and the implosion pulse are exactly the same, and the echoes here are the same position, and the direction of the echoes are the same position, even though the top shot on the top was created by explosion and the shot on the bottom was created by implosion. And if you look, after the shot travels for a while, the echoes, these are repeat echoes. These repeat echoes don't have all this fuzzy stuff on it, which we call noise. And so the noise would be the high frequency echoes created by the energy in the shot. And as the shot travels, usually over 3,000 feet, you start to lose all the high frequency signal. And even here, the repeat echo of this was a repeat of that. This is a repeat of that. They look exactly the same. Well, hold on, they're not exactly the same. The explosion shot is bigger. That means it has a higher amplitude. And one of the reasons likely that it's a higher amplitude is because the pressure is higher, twice as high as the pressure here. And so this kick is more amplitude than that kick right there. So this is not only an example of direction kick, but you can see a marker being used here in the tubing. It's been used from a distance to liquid. And you can see the idea of a repeat echo. This echo is repeated here, and the lick level is repeated here, and the time from here to the lick level is exactly the same time from the lick level kick to the repeat of the lick level. So repeats travel time is the same exact time as from the initial blast from the shot to the echo in the well. All right. So what does it take to make a good shot? Well, what it takes to make a quality shot is, well, the first thing is stabilized conditions. Now, you can take a fluid level shot on a well, even though the well conditions may not be stabilized, but that means likely that the fluid level is changing position, and the pressures are changing, so the well is not stable. So when we go out to analyze a well for continuous operation or steady state conditions, we want to make sure that the conditions that we assume with our data we collect are represented by the well's condition. So we should take a shot, and we should see a clear lick level kick. If we don't see a clear lick level kick, then we may need to make some kind of change, maybe the charge pressure in our gas gun or the way our gas gun is connected to the well. But there's things we can do to improve the echo from the liquid level. Now, once we've acquired the fluid level shot, we typically, by default, the automatic analysis method is to count the tubing collar reflections. So we assume that there's tubing collars in the well, and the echoes are uniformly spaced, and we assume that you've entered the average distance between the tubing collars, and then we count them and use the average joint length to determine the distance to the liquid, and we determine how fast the pressure wave went, the acoustic velocity. And so if you don't have a well that has, if your well doesn't have a 31.7 average joint length, that's the default from Echometer, then you need to put your well's average joint length into the software that you use to shoot the flood level. Now, the deviation survey is important because the pressure wave travels along the pipe and is measured depth. So the echo goes the length along the pipe, the measured depth along the pipe. That if we're wanting to determine the pressure at the pump or the pressure at the bottom of the well, then we need to have a deviation survey that is used to convert the measured depth into true vertical depth. The casing pressure is important because if we're wanting to, and the pressure typically is automatically measured by the pressure sensor on the gas gun. And so the pressure sensor is used. It should be calibrated before you put pressure on it. It should be zeroed before you acquire data. So we take the calibrated pressure transducer from Echometer, we do a 0, and then we use that to determine the pressure at the surface of the well. And that pressure is then used in the calculation of the pump intake pressure, the pressure at the gas liquid interface, the pressure at the bottom of the well. It's also used in the calculation of acoustic velocity. So the pressure is important. And then the casing pressure, or the pressure at the surface of the well, is continued to be measured over time, typically at a time of 2 minutes. And that change in pressure per time is used by the software to automatically calculate how gassy the fluid level is. So if the pressure builds up, the software assumes that the surface builds up. We assume that there's gas is flowing into the annular space below the surface, and that increase in pressure is a function of the gas flow rate and the amount of liquid in below the liquid level. So the measurement of pressure also helps determine the gradient below the liquid level and the pump intake pressure. The tubing casing sizes are important because we use the areas to calculate the gas flow rate. So we need to know tubing casing size. The weight of the oil and the weight of the water is determined versus depth by the input gravities of the water and the oil. So those should be typed in. Or they're defaulted at 40 degrees API oil and 1.05 water gravity. So if your well has different conditions than the default, then it's going to calculate incorrect pressures. So you need to make sure that your properties of your fluid are typed in. Typically, the software uses the acoustic velocity to calculate the gas gravity, and then the density to calculate the weight of the gas down to the liquid level. Then the last bullet says we should always take 2 shots. Even if the first shot is a good shot, it's always good to take a second shot and to make sure that the echoes repeat. Normally, when you take a fluid level shot, the most time that was consumed to determine that fluid level shot was the time to drive to the well. And so once you're at the well, the time to take another shot, a couple of 2 or 3 minutes later, is not very significant in the total time. So it's always good to take 2 shots. That'll answer your questions and not have to go back to a well and take another shot sometime. Now we're getting ready to start talking about the direction of kick on the acoustic trace. And the echo, whether it's an increase or a decrease in the Wellbore, determines the direction of kick on the reflected echo from that, let's call it an anomaly. When you have an explosion shot, a reduction in the cross-sectional area of the Wellbore echoes back as a down kick, because the explosion shot is a down kick, and a decrease in cross-sectional area echoes the same direction of the shot, a down kick. When you have anomalies in the Wellbore that decrease and create an echo that's a down kick, they would be things like a liner top would be a down kick, a tubing anchor would be a down kick, some kind of blockage, maybe paraffin, scale, both of those could be blockages, and then the liquid level, all these would be down kicks as examples. Now, when the Wellbore gets larger and echoes displayed as an upkick, those could be holes in tubing, perforations, open hole, sliding sleeve that could be open, a sliding sleeve that would be closed may not make an echo. Parted casing, which you would not want, or parted tubing, which you would not want. And if you have a liquid level below end of tubing, you'll see an upkick at the end of the tubing. So these are the perforations in the hole in the tubing or hole in the casing, they look a lot the same, but a perforation is a known depth typically, and you'll see the echo, the upkick, at a known location of perforation. But the hole would be an upkick that would show up, and you'd have to say, well, that echo just doesn't belong there. And so you need to sometimes investigate echoes that don't relate back to changes in cross-sectional area on your Wellbore schematic. Now, the implosion shot, the way we explain it, sometimes is confusing. And so the most important thing to think about when you do an implosion shot is that you need to tell the software whether you did implosion or explosion. If you tell the software that you did an implosion, then the decreases in the wellbore will be displayed as downkicks, just like the decreases in the wellbore would be displayed by an explosion shot. So that you telling the software it's an explosion or implosion makes the kicks, up kicks and down kicks, have the same direction when you're analyzing the data. This is a diagram that's starting to show wellbore. This is a casing, and we're shooting on the casing, and we did an explosion shot right here. So we start off with a down kick, and the acoustic wave travels down the well, and it encounters a decrease. Let's call this a liner top at 3,000 feet, and so it echoes the same direction of kick, a down kick, at a decrease, and then a portion of the signal travels past the liner top into this smaller diameter tube, and when it hits the bottom, it's also a decrease, so it echoes a down kick, a decrease in cross-sectional area at the 5,000 foot depth. Now this is an example of a casing that's constant diameter, and inside we have a tapered tubing string, and when we shoot an explosion shot, we create a down kick, and a down kick travels down the well, and when it reaches this point, the wellbore expands or gets larger, and that inverts the pressure wave and sends an inverted signal back to the surface. So it starts off with a down kick, and so it inverts the kick back to the surface as a up kick, because increase means kick up. And then some of the traveling wave continues, energy travels on back down, hits the end of the tubing, and it shows up as an up kick. Now, this distance from here to here and this distance from here to here are exactly the same. And so now we have this kick here that's a down kick, and where did it come from? Well, the echo of the up kick travels back to the surface, and it doesn't just evaporate when it's a surface, it goes back down the wellbore. And it's an up kick coming down the second time, and when it hits this increase in cross-sectional area, it inverts the signal and sends an inverted up kick, which is a down kick, back to the surface. So this kick right here is the repeat echo of the increase in cross-sectional area in the wellbore. And so often that's confusing, but the idea is that when you have an increase in the wellbore, it inverts the signal. And so this is an inverted signal right here, and that's an inverted signal. So we send a down kick, it hits the increase, inverts the kick, and echoes back to the surface, an up kick, and the up kick travels back down the well and hits back to the surface once it's been inverted as a down kick, the same exact round trip travel time. So someone will probably have a question about this. This is a FLILO shot in a shallow well, coal bed methane well, and you can see the shot going off here at time 0. You can see these little sharp kicks, and those are high frequency echoes from the collars. And then you can see an up kick right there, which is a perforation, another up kick right there, which is perforation, another up kick, which is a perf, and then a liquid level. Now, the direction of kick, these 3 echoes are up because there are increases in cross-sectional area and this kick right here is down, and that's a decrease in cross-sectional area. Now, when you can access the data that we're using for the presentations, and you install it on your TAM, in TAM, there'll be a folder created called downhole marker, and the name of this file will be fluid level PFL downhole marker cold bed perfs. So here, this is what the acoustic trace without the wellbore shows. If you overlay the wellbore, then now we've got a mark on the wellbore that shows a perforation, another perf, and then you can't really see the perf marker right there. But now you can see that this upkick, the beginning of the upkick, right at the knee, right where it just first bends, matches that perf, that mark. The upkick right there matches that perforation. And this is the perforation that we use, the deepest perforation closest to the liquid level, to determine the distance to the liquid level. Now, if we were to go back and just jump back to this perf, we would see that this perf lines up perfect, but this one doesn't quite line up as much, and this one doesn't quite line up as much, because the acoustic velocity changes with pressure and temperature. So as you get deeper in the well, the temperature going up, increasing, and the acoustic velocity is slightly increasing. So whenever we determine the distance to a liquid level, we want to always try to use the deepest marker that's closest to the liquid level above the liquid level to determine the correct distance. So here, there is perforation at 1369, that kick right there. There's the perforation at number 2 at 1531, and this is a perforation at 1808, and then there is our liquid level at 1887. Now this is the same example here, and it's showing the perforations. These perforations are only 2 foot wide, and you kind of see the perforation that's closest to the surface has the biggest echo, and then next perforation, which is a little bit wider. This is 2 foot. This is 3 foot. It's a little bit wider echo, and then the perforation that's the deepest is the shortest amplitude, partially maybe because there's some liquid flowing out of that perf and it's partially blocked. But I'm not sure exactly why it's so much shorter. It seemed like it should just have gradually decreased. This is a well in North Dakota at the bottom, and this one is downhole marker fluid level casing weight change. And so we have right here a green line, and this is a marker that the user typed in, versus this is a marker up here in red that the TAM software used from the Wellbore schematic. So this is a Wellbore schematic marker. This is a manually entered marker. So if you want more information on a marker, there's a lot of detail here. It says Wellbore from 26-pound casing to 38-pound casing at 5913. That's the depth of 5913. The ID changed by about 1/3 of an inch or 1/6 of an inch on the side. And so you can see with this little echo right here, due to casing weight change of heavier weight casing, that right there is a down kick when the wall of the casing got slightly larger by 1/6 of an inch all the way around. So you could say, well, I can see a 1/6 of an inch increase in casing size over a mile away, 5,913 feet away. Now this is that same well that we just talked about with the 3 sets of perfs, and you see the liquid level is below all 3 sets of perfs, and so by shooting the fluid level you can say, well, there's no back pressure on this formation from the liquid. My cold bed is not being restricted by liquid. It's just being restricted by, if any, by the casing pressure. And so the casing pressure is restricting the flow, but the liquid level is below the perforations. You can see that the pump card shows that the pump's half full. All right, so this is a well out in West Texas. It's a Rotaflex well, and it's showing the same. This is the same acoustic trace on both traces. This one is using the downhole marker method, so I'm using the perforation right there, the upkick of the perf, to determine distance to liquid. And this marker, this top perf at 7669, is very close to the liquid level. The software stopped counting collars automatically about 5,300 feet. So the deeper you count the collars, the hotter the gas would be, and the higher the average acoustic velocity would be. So this gives us a little more accurate distance to liquid because we have used a marker that's closest to the liquid level. But even then, we're still, even though we didn't count collars very deep in this well, we're still just 15, 16, a half of a joint in error. So often when someone asks me how accurate a fill level shot would be, I'd say usually we are able to get more accurate than a half of a joint, and that's just a common error on an easy fluid level, about a half of a joint. Now these are some hand-drawn examples of different wellbore configurations. This is like a coal bed well in Kentucky where they've come in and reamed out the coal seam, and it's a big cavern down here. And so the change in cross-sectional area right here is large compared to the coal that's the casing. And so the amount of energy that passes is, or the amount of energy that's reflected is a ratio of the cross-sectional areas. So this area here is small, and this total area is large, so almost all the energy gets reflected back to the surface at this top of this cavern. So it's very common when you have a really big cavern or big wellbore below the case into the tubular casing to not be able to see the liquid level. And so this case right here, we don't really show an echo at the interface of the liquid level because almost all of the energy gets reflected right here. Now this well has liquid flowing out of some top perfs, and it's showing the liquid level down here, and when we shoot the flow level, there's so much liquid flowing in that you just see a liquid level at the perfs. So this is unusual because most of the time when you have liquid flowing in at a very high rate to fill up the wellbore, then the liquid rate is very high. If you have a very high liquid rate that fills up the wellbore, then the liquid level would likely be filling above the well, above the pump. So this could be like a casing leak. This could be like upper perf zone. But it says you're not seeing the liquid level below the top perf because liquid's flowing up in very fast, filling the cross-section area of the wellbore, and we're not seeing liquid level kick. But almost never this happens because most of the time when liquid flows in so fast that it fills the entire wellbore cross-section, you can't see past it, then the liquid level fills high in the well above the, let's call it casing leak. This is more common. Whenever you shoot a flow level, you have an upper set of perforations. Almost always, unless there's scale that plugs the perforation off, you almost always see an upkick at the top perf. And so this is common to see the top kick perf, and the top perf is almost always a good downhole reference for a downhole marker. And then we see the liquid level below. This is a well, it's called PFL, static gas well offshore. And we see that there's a subsurface safety valve right here, and there's I think that's called a polish board receptacle right there, and then right here is the liquid level. And so those are our three primary kicks. But when you shoot the flow level, the subsurface safety valve traps some of the energy between the surface and what? This echo is trapped, so this energy from this echo is trapped, and it bounces back and forth. And this is called a repeat. And then when the polish board receptacle hits the surface, some of its energy is trapped, and it repeats and repeats. So those are repeat kicks. And the liquid level does the same thing. The liquid hits the surface, and it gets trapped. That traveling wave from the liquid level gets trapped, and it echoes. And so when we have something high in the well that has multiple, repeat echoes, then you're going to have repeat echoes off your other echoes from your well, and you need to identify those and ignore them in your analysis. So these should be ignored. They're not echoes from something that's at this depth. They're repeat echoes from something high in the well. Now this is a fluid level shot on a gas lift well, and we call it conventional gas lift wells, where the gas lift mandrels are ran on the outside of the tubing, and to be able to remove the gas lift valves, you have to. They're really not even gas lift valves. They're typically just gas lift. They're gas lift valves attached to the outside of the tubing. There's really not always really a mandrel. Mandrels usually are tubing retrievable wells, and they're not typically called conventional. So the gas lift valve sticks out and makes a big echo, and so you can see kind of a fuzzy thing right there, some noise there, noise, noise, noise. And if you turn on the low pass filter, then the software smooths out the echoes so that any echo that's narrow, high frequency, gets smoothed out, and then the big obstructions like this gas lift valve, they show up. And if we overlay our wellbore, we can see that the gas lift valves are marked on the tubing, and you can see the upkicks of the gas lift valves correspond to the location of the gas lift valves in the well. And so I've labeled here, this is gas lift valve number 1 from the downhole marker screen in TAM. And then there's gas lift valve number 2 and gas lift valve number 3. And then gas lift valve number 4 is basically where it's just right, very close to where the liquid level is. And so likely you're operating off the orifice at the bottom of the well, but your fluid level is right there at that depth. Now you might notice that this marker right here is kind of cuts right through the middle of this little symbol that represents the gas lift valve. And you can see up here that the marker, the acoustic echo, doesn't quite center through the gas lift valve. And so that's why that happens, is because the acoustic velocity average to the bottom gas lift valve is faster because this gas is hotter than this gas from here to here, and so the acoustic velocity is slower. So the gas lift valves typically only line up on the previous and the current marker that you selected, but the average is correct. But the average here, from here to here, is slightly slower, and then down here, the overall average is faster. This is a well out in the Permian Basin, and it's not very deep well, and that makes the echoes strong from the shot that you make in the well. And this well has a tubing anchor, a liner. You can see how the casing goes in a liner. It has some perforations out in the horizontal. It has a bunch of echoes: down kick, down kick, down kick, up kick, down kick. So when you look at this, usually we say, well, the deepest down kick's the liquid level. That's what you usually say. But in this case, that's not what's going on here. And so we can see that the marker for the tubing anchor is right here, and this kick right here, the tubing anchor, is our reference, our downhole marker reference for depth. And so if we look, we can see the down kick of the tubing anchor right there, and that's what we use to determine distance to liquid level. And then we can see the liner top right there, and then we can see the liquid level right at the end of the tubing, which is typical for a pumped off well. Okay, and there's our distance to the liquid level based on the distance to the tubing anchor. And then this pressure wave of the liquid level has to travel back out of the liner. And so as it travels back out, it's going to see an increase in cross-sectional area, and it's going to be a upkick. And so this is travel time here, elapsed time. And so from here to here is the time back to the liner top. And so there's an upkick at the liner top, and this upkick's not the top perf. So sometimes when you analyze this, if you don't think and match up your markers, then you might have said, well, that's the top perf, and that's the liquid level, which it's not in this case. This kick is just another repeat kick from the liner top back down to the liquid level, so it's kind of gets trapped in that space. All right, so when you have a liner, you typically see down, down, and then you see an upkick, and the liquid level is in the middle. And so this upkick of the liner top going back out is not the top perf, and that's not liquid level, it's just another repeat. So liners and tubing anchors all together can make an acoustic trace confusing. You also can see the tubing collars right here, the echoes from the tubing collars, and they're not quite. This diagram is the collars aren't spaced so close that you can't see them because it's a shallow well. Also, this is the horizontal portion of the well where we have the horizontal section of the well where there's a long perforated interval. Another well with lots of echoes. So we see a down and a down and a down and a up and a down. Oh man, this gets pretty confusing. And so this is the biggest down kick, so we probably pick that as liquid level, but it's confusing without trying to match it up with your Wellbore overlay. So once you display the Wellbore overlay, now we can see this down kick is a tubing anchor. And notice it's a very narrow, sharp kick. That's kind of common because the anchor doesn't take up a lot of space. So it's a sharp, narrow kick. Usually anchors aren't a big kick compared to liquid level. Now the liner is a down kick. There's our liner, and it's at 4384. And then this is somewhat unusual because this is the top of the oversized downhole gas separator. And so there's the down kick at the top of the oversized separator, and there's an up kick at the end of the tubing, and there's the liquid level. And so in this well, this operator was doing a special test, and this well produces quite a bit of gas, and so they shut the casing in, let the casing pressure build up to move the fluid level to figure out which of these echoes was the actual liquid level. And they push liquid level below into the tubing, and there's our liquid level. And so we have tubing anchor, liner top, oversized gas separator, end of tubing, and liquid level. And this is probably a repeat echo fluid right there. All right. There's our depth liquid level of 5,021 feet. So the overlay helps a lot to be able to figure out complicated anomalies, the downhole markers, changes in cross-sectional area in your wellbore. This is a well that has 2 different liners in it, and it has lots of echoes. And someone sent this data to us, and they said, how do we figure this out? There's lots and lots of echoes, and it's hard to figure out. Well, this was data before we even had the TAM software, and we said, well, one of the things about a liner, you look for a down, down, up, and the middle down kick here is going to be the liquid level. And so liners always have that distinct signature when you've identified liquid level, because it goes. So let's turn on low pass filter first. There's low pass filter, and it takes all that high frequency noise away. We see a down kick here, a down kick there, an up kick. And so immediately we think, well, this is probably the liquid level here in the middle, because this distance here from here to here, and this distance from there to there are exactly equal. And one feature that you could use to show that is TAM has an option to bend the acoustic trace, fold the acoustic trace at a kick. And so long ago, when we used paper strip chart recorders, often the operator would take a paper strip chart and fold it at a kick to see if 2 kick echoes matched up. And they could use that as a technique. And so in the TAM software, we've added that technique to allow you to fold the trace. And we'll show that when we go back into after this presentation is over, we'll show that as an example how you can do that. So this is a liquid level, and all these other kicks are just repeat echoes. And so right off the bat, once we've identified that, we can see that here's our liner top, here's our liquid level, and then down at the liner top, down at the liquid level, and then this distance here, this time from here to here, and that time from there to there, that kick right there is the repeat of the liner top as the pressure wave goes back out of the liner top from a small diameter to a large diameter. it's an increase, and so it creates an upkick right there. And all these other echoes are just repeat echoes. All right, high fluid levels. High fluid levels are difficult because the software usually ignores the acoustic trace that during the first 1 second of the fluid level shot. So when that happens, and the TWM or the TAM software can't pick the liquid level, then usually it'll put the liquid level right at 8.5 seconds. So right here on this acoustic trace, the liquid level has been selected by the software at 8.5 seconds. But it tells us, it says, the automatic liquid level detection failed. You need to manually relocate the liquid level marker. Now, this example is a very high fluid level very high. And the hand-drawn example up here is what it's trying to show you is that if you use too much pressure in your gas gun and you create a resonating sound, all you're going to see is this resonating sound, and it's going to be difficult to count the color echoes. And if you use just the right amount of pressure, differential, then you may be able to create the shot going off and little color echoes and then a big echo at the liquid level. That'll take a lot of trial and error, but that you can do that. But it's usually pretty difficult when the fluid level is within 2 or 3 joints of the surface. If it's deeper, it's probably easier to see the colors. So if we go in and examine this liquid level, we say this is a liquid level screen, and we want to pick it. Well, I don't see a downkick right there. So when you look at an acoustic trace and the program has automatically selected liquid level, and you look there and you've been used to the software picking the liquid level, you have to say, I don't see a liquid level right there. The software goofed up. You can't say the software is smarter than me. I know there's liquid level there. There's no liquid level downkick right there. So what do? Well, you say, look, I can see a repeating echo. I can count these 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10. So the liquid level is a repeating, and there's 10 repeats per minute. So the liquid level is up here about 1/10 of a second from the surface. One other thing you might notice is the round trip travel time, the joints, acoustic velocity are all displayed as unknown. And when the software doesn't determine the distance to liquid level, it leaves the fields filled with asterisks until you move the liquid level indicator to the right location. So here we've moved the liquid level up close to the surface. Here's the shot going off, and this distance is 1.04 seconds. So this is the acoustic trace from here to here blown up, and we're seeing this high fluid level 1.104 seconds from the surface. It's a shallow liquid level. Sometimes to see a liquid level like this, you have to use a very small differential pressure, or there's so much energy shot into a confined space that it causes the microphone to turn off and absorb the energy. So you have to adjust your charge pressure in a lot of cases when fluid level is high. This is another example of a well with a high fluid level, and we see here that the software automatically picked the liquid level. Well, did it pick it right? I don't know, because look, there's a repeat and a repeat, and those repeats are close together, and this isn't half, this is twice this distance, so I better use the scale down button and scale the acoustic trace down so I can see that there's the liquid level, and this is the repeat. The software ignored this one because it was in 1 second of the shot going off, and so you take your mouse and grab a hold of the liquid level and drag it back to 0.628 seconds, and that is the liquid level kick. And in this case, you can see there's some color kicks, and so when the fluid level is about 300 or 400 feet from the surface, and it's still less 1 second, there's going to be some color echoes you can probably use to determine distance to the liquid level. But if it's really close, you can't see the colors very well normally. Now this is a fluidable shot down the tubing, and this is a well that's called plunger hole at 4325. And so when you shot down the tubing, you see this upkick, and this upkick isn't supposed to be there because in the wellbore there's no increase in cross-sectional area at that depth. So normally when you go to a gas well, you shoot down the casing first, and the fluid level should be at the end of the tubing. And if the fluid level is higher than the end of the tubing, that can mean that the gas is flowing up the casing through a hole in the tubing, and that high fluid level is indication of a possible hole. So then you close the well in, build pressure up, push the liquid level down, and you can shoot till you see an upkick. And then once you see the upkick, you move your gun to the tubing and shoot down the tubing. And if the upkicks are at the same depth, they may not be at the same time because the gas has different possibly composition, or maybe different pressures, and so they won't be exactly at the same time, but they will be at the same depth. And there's an upkick right there that matches. This is a rod pump well up in Oklahoma, and the operator that collected this data called and said, "Hey, I've got this pump car that's full of liquid, but no liquid's coming out the tubing." And we talked about it and said, "Well, when you shoot the fluid level, do you see a down kick when the pump's running?" And he said, "Yeah, there's a little down kick above liquid level." And so we agreed to turn the well off for about 50 minutes and wait for the liquid to run out of the tubing above the hole. And then he shot it down the casing again, and he saw an upkick on the casing. He saw a down kick on the casing shot when it was pumping. So this is an example of only shooting down the casing. But he could have also shot down the tubing, but we didn't talk about that. That's a long time ago. We've written a paper in 2014 that talks about troubleshooting rod pump wells by shooting down tubing when there's no production on the surface. And this example here is downhole marker leak tubing hole. So that paper will be available from our webpage that you can download and learn additional information about shooting suck rod pumping wells down the tubing, looking for holes when there's no production of surface. Now this is the dynamometer card when the well is pumping. The pump card is not very tall, which means it's not picking up much fluid load, and so the height of the pump card is directly related to the lift to the surface, and so this is the height, and this is the lift of the liquid above the liquid level, and it's liquid is squirting out in the casing annulus, and it created this little down kick right here when the well was pumping. So this distance here represents the lift of the well, and there was no liquid to surface, and so we could see the down kick as the liquid squirted out the hole in the tubing into the casing annulus. This is another suck rod lifted well, and there's no production of the surface. It's not obvious that there's a hole, there's no upkick. But if we turn on the low pass filter, we can see an upkick right there. It's a hole near the surface. And then this is the time from here is the time to the hole, and then the repeat is the same time. There is the repeat. It's inverted, so it's an up kick first, then down kick. So this is shot down the casing, and it identifies. We can see the up kick, and then when we shot down the tubing, we can see that this one has the overlay of the tubing shot in blue, and the casing shot with the low pass filter, and we can see that the upkick on the casing shot and the upkick on the tubing shot line up, and these echoes right here are the couplings holding the suck rods together, and the average joint length is 25 foot shot down the tubing, and the average joint length down the casing is at least 31.7 feet. And you can't count the collars down the tubing because typically, unless you change the average joint length. So you have to be careful when you shoot down the tubing on a suck rod lifted well to use the acoustic velocity from the casing shot, or typically the upkicks won't line up because you have more echoes in the tubing because the suck rods are typically only 25 foot long. So in this case, the hole's 263 feet from the surface, and you can use acoustic velocity on the tubing shot, and the upkicks line up. Now, this is a well where there's no production of surface, but they pressure test the tubing, and this was shot down the tubing, and there's an upkick, and the pressure test of the tubing held. And so, what is this upkick? What is this? And so we spent quite a while trying to figure this out because there wasn't. It was a hole because the pressure test was hole pressure. And we overlaid the wellbore, and after looking at it for a while, we realized that at a depth of 2,000 foot, that this upkick is the increase in the tubing cross-sectional area because it's a taper, and tubing tapered from 1-inch suck rods. So I said tubing taper, suck rod taper from 1-inch suck rods to 7/8-inch suck rods, and so there's an increase in cross-sectional area right there, and that upkick corresponds to the top of the tubing taper. So that was kind of a surprise. I didn't expect to see the upkick, and we saw it. And so there's our top of our 7/8 suck rods, or the bottom of our 1-inch rods at 2,000 feet from the surface. When we display the acoustic trace along with the Wellbore diagram or Wellbore schematic, when we match up the echoes with the anomalies on the tubing or the casing, that improves our ability to analyze the well. We can see the direction of the echo, which helps us identify each change in Wellbore cross-section, whether it's enlargement or reduction. It's important to have an accurate Wellbore schematic entered into your well base file, or your view of your wellbore. If you count collars, and the software automatically always counts collars, it's important to use the Echometer default average joint length, but to use the correct average joint length based on the joints of tubing in your well, the average of the joints tubing in your well. And if you identify a marker closer to the liquid level than the collar count is close to liquid level, then the marker, or the automatic collar count method, or the C line that says collar count, I didn't identify that. We probably ought to go back and talk about that. The deepest marker is the most accurate distance to liquid, and that's what it says here. Which one should you use? Whichever is closest to the liquid level. If you're interested in additional information about fluid level, acoustic fluid level measurements in oil and gas wells, then Dr. Podio and Jim McCoy have written a book, and that book was published in 2017. And there's a link right here that you can click to go to Amazon and purchase that book. It's a very comprehensive discussion on fluid levels. So with that, I'm open for any questions. Gustavo, do you have questions that we need to answer?
Yes, we have a few questions. Thanks, Lynn. We have a question from Mo Yunus asking, how can we know or detect a tubing leak with Echometer? And there's a second question related from him. Can the tubing leak be detected if the leaking is below the fluids?
Two questions. That's a good question. So all right. So this picture right here is a hole in the tubing where there's a tubing leak, and we shot the fluid level and we could see the upkick, and we shot down the tubing. This is a casing shot. We shot down the tubing, and we saw the upkick. But in this case, the liquid level is much deeper, and so the liquid level of the tubing is deeper, and so we can see this upkick in the tubing. But if the liquid level is above the hole, then this paper talks about that some. So you might want to download this paper and read this paper, this troubleshooting rod pumped wells using tubing fluid level shots, because one of the things it says is that when the well's pumping and there's no hole in the tubing, then the liquid level is going to start to typically go toward the surface. Typically, the fluid levels are within a second of the same depth when the hole is below the liquid level. So you're circulating fluid through the hole as you pump, and the liquid level in the casing and tubing usually stabilize close to the same depth. So there's several indicators that you can use to identify that there's likely a hole. One indicator is that if there's no hole, the fluid level will pump up toward the surface, and that's talked about in the paper. And another indicator is that the liquid levels are about the same depth. If the hole is above the liquid level, then it's going to show up as an upkick. Here on page slide 21, this is a gas well. That upkick was above that hole, and tubing is above liquid level, and it shows up as an upkick. So that's typically what you'll see. Did that answer the question? I guess that probably answered the question.
Okay, yes. And well, it also made a second question asking if the tubing leak can be detected if the liquid or the leakage is below the fluid level.
Right. So if the hole's below the fluid level, then the well circulates the fluid through the hole, and the liquid levels become close to the same level on the inside and outside, and that's discussed in the paper. And so you really can't see the upkick anymore if it's below the liquid level, but you can see some symptoms. One symptom is the fluid levels are about the same. Another symptom is when you pump, the fluid level won't go up the tubing; it'll just kind of stay the same depth. Another symptom is, well, no production of surface. So there's several symptoms, but you don't see the upkick.
Yeah, and there is a question kind of related to from Bridget Walter asking, can you get echoes from features below the liquid level?
Normally the answer is no, but in some wells where the fluid level is within about 15 feet or less from the surface, then the fluid level then the pressure wave can travel into the liquid. So normally we say that all the energy from the shot reflects at the liquid level, but when the fluid level is near the surface, then all the energy doesn't reflect, and some of the energy goes into the liquid level, and you can see below liquid level, but it has to be a special case. It has to be fairly dead well, no gas, pretty much gas-free fluid column, and you can see then if it's very close to the surface when you shoot the fluid level.
Great. And we just got a question. I'm gonna bring it in because it's related to holes. Then Hamdi from Tunisia is asking if the hole matches a color, can it be detected?
Well, the answer is, if the hole is a hole, the answer is yes, because you'll see an upkick at the collar. But if the hole is just a leak through the threads, then the answer is no. So I have examples of tubing where the hole was an 1/8 inch diameter and it showed up. So the answer is typically you'll see a hole, and if it's a quiet well and you've got some pressure in the well, then I'd say you'd see holes down, tiny holes, maybe even a 1/16 of an inch in diameter, not very big. I think the answer would be in most cases yes, but if the hole is a seep through the threads, you won't see it.
Okay, we had a couple of more questions. One of those is related to the TAM software from Andres Solano, and he is asking, why is the all colors mode disabled when the round-trip travel time is below 1.4 seconds. Why 1.4 seconds?
Because it's difficult. Okay, let me show you an example here. If we go to the shot that, yeah, this kind of shows even here. Notice how at the beginning of the shot, there's this energy from the shot going off that's shifted away from the zero. And so the more energy in the shot, the more of a shift you see due to the pressure, energy from the gun, shifting the acoustic trace. And so that one shows it. This one's you can't see it here, but if you put the term low pass filter, see how the beginning of the shot it's not centered on zero, and so when the fluid level is, we typically ignore automatically counting collars less than 1 second. Now, I'm not sure about the 1.4 seconds.
1.5. It's 1.5 is what the software is doing. Below 1.5.
Well, this was we usually say 1 second. I don't know if it's always 1.5 or 1.4. So there may be some other condition that's at 1.5.
We have a question asking for what would be the right charge pressure, and I'm assuming that's related to how much pressure we can charge on the.
Okay, that's a very normal question. And so when you read the manual from Echometer or a technical reference, often Echometer will say 150 to 200 psi above the well pressure. That's a place to start. And so we should say something like the starting pressure for your first shot should first try between 150 to 200 psi pressure. But if the well is deep, if the pressure is very low, if the well is noisy, then you need to put enough pressure in the gas gun to make a good echo. And so the amount of pressure charge you use depends on the well. If the fluid level is less than 5,000 feet and the well is quiet and it's not pumping and the pressure is fairly high, maybe 25 psi pressure would be enough differential pressure to make a very good kick. So when the fluid level is near the surface, if you put too much energy in your shot, then you just get a lot of noise. So you have to, high fluid levels use less pressure, deep fluid levels use more pressure. If you don't see a good echo, put in more pressure. If you think the fluid level is high, put in less pressure. You'll get an idea after shooting fluid levels on wells what a reasonable pressure to use is. So maybe one guy in one field has to always use 1,000 psi of differential pressure to shoot the fluid level, and another person always just uses 100 psi, and that's because the well conditions are different, and so you have to adjust your well pressure based on your well conditions.
Great, thanks. We have one more question. It's kind of interesting one from M. Pierre. He's asking, if a well has a packer, would you recommend taking a static fluid level inside the tubing, and how accurate is it?
Well, that's a good question. Normally, if a well has a packer, it's going to be a gas well or a gas lift well or a well that has some kind of leak. And so when you shut the well in, if the well is a gas well, then the gas pressure typically increases. And if there's no standing valve in the tubing, it pushes all the liquid out. And this fluid level will be down in the perforations. And so a lot of wells that you shoot down the tubing, if there's no obstruction in the tubing and no standing valve, then typically there's going to be a lot of gas production, and not always, but typically. And the fluid level will be very accurate, and the pressure is going to be accurate, and it'd be a good test. Now, if you have a standing valve in the well, so again, this again depends. It depends on the producing lift method. If there's a pump in the well, usually you can't shoot down the tubing and get a good static. So if a pump was going to block the pressure wave, it's going to be difficult to see past the pump. You can't shoot a sucker rod lifted well for a static because the standing valve is going to block the shot. But if you're a flowing well, the standing valve will tend to trap the liquid, and if it's shut in for a long time, the pressure of the standing valve is going to be very close to the same pressure, and it'll probably be a good shot. So I'd say yes, if you're shooting down the tubing on a gas lift well or a plunge lift well or a gas well, it's common to shoot down the tubing and you get an accurate static bomb pressure. The assumption of the software is the liquid in the tubing is based on the production rate. So if it's 10% oil and 90% water, and you have liquid above the end of the tubing, we're going to divide the gradient based on the production.
We have another question here. It says, are there any instances where I may need to adjust my depth determination manually?
That's a good question. The answer is yes. Normally, you would want to manually adjust your depth determination. So the programs, the software, the TAM software, TWM software, automatically count colors by default. Let me bring up TAM and show an example here. So here's the TAM software on the screen. And if I were to go into a flitable shot, let's get an example. This is an example that we talked about. It was a Rotoflex example. Okay, and here's our flitable shot. And this is a rod pumped well. It has a tubing anchor in the well, and it counted collars down to here. Okay, so there's our collar count. So when the collar count isn't 85 to 90% of the depth of the well, then you should probably reshoot the well or manually adjust the selected interval to see if you can get the more collars to be counted closer to the liquid level. So here's our liquid level right here. So the question is, do you adjust it? And so in this case, yes, because the collar count's not very deep. If your collar count is always right down to the perfs, then probably the automatic method is pretty accurate. Now, so if we go in the collar count method in TAM, you can see here that we have the interval from 4.5 to 4.5 seconds selected. And that's what it says here. That's this interval right here. And as we move this interval, it's going to refilter the signal. And it may move this collar count line. So as I move it deeper in the well, the collar count line is not moving any deeper in the well. But now see there, these collars, I can see a collar there, collar there. So that's not a very good collar count. So I adjust that there to line up the first collar. And then adjust it. So you can adjust. So if this collar count line automatically moves down deeper, that's probably good. So see, I moved it here and it's not matched. There's no, the C line disappeared. Let me see. You all probably can't see that very well. So if I expand this out, move to a different interval. See, it came back. You can see that there's a pretty decent kick there, collar, maybe collar there. So I guess the answer to your question is, if the collar count line, the C line is not very deep, then probably you should either reshoot the well or manually select a different interval. That would be my recommendation.
I think Sean has a question for you.
Yeah.
We can hear you now. Go ahead.
Okay. Hey, I appreciate you putting this on. I got a question for you, Lynn. Shooting down gas lift wells while they're still injecting, I typically prefer to shut the injection gas off just to minimize the noise, but sometimes you've got a compressor on location, and if you shut it in, you're gonna knock the compressor offline and have to get someone out there to start it back up. So, but if you take a fluid level shot while it's still injecting gas, the acoustic velocity as it's traveling down the well is going to be traveling faster than normal, right? Due to the injection gas. And then conversely, on the way back up the hole, where the wave is coming up against injection gas, it's going to slow down, but in the balance, does that all net out? And it's going to be the normal acoustic velocity would be if you shut the injection gas off?
Sean, that's an interesting question. You know, normally don't really think about the gases moving. We just assume that the in situ gas has a certain pressure and temperature and has an acoustic velocity. So, you know, I don't think I've ever done any kind of study to see if the acoustic velocity going with the gas is faster than the acoustic velocity coming back up.
But it should, I guess, give you the same overall acoustic velocity, correct? I mean,
yeah, I think it's got to be it's average acoustic, average round trip travel time, but I don't think it would really matter, and I don't think the velocity is normally that significant because that would be my guess, because the acoustic velocity in gas is in terms of 1,000 to 1,500 feet per second, and the gas velocity of travel is probably not that fast, so it probably quickly moves the gas relative to the gas velocities would be my thought.
Okay.
But if you got some data that shows that, I'd like to see it.
Yeah, I don't know. I mean, I typically, like I said, if I can, I shut it off. You just get much better quality data, taking all the noise of the injection gas off. But I've got some customers that have compressors on location, and if I shut it in and knock them down, I got to call the pumper or somebody out there to go kick them back on, and they usually don't get too happy. You know, I prefer to get better data, but I also like to keep my customers happy. So
we have a presentation on acoustic velocity of natural gas and troubleshooting gas lift wells. I think that probably in the future we'll probably do that presentation as an Ask Echometer presentation. So that's probably on our list fairly soon. So that'll be a presentation that we'll make, and we for sure would like you to send us some data that would show that when the gas injection rate's high, that the velocity down the well and up the well is not the same.
You know, you'd think if it's speeding up the wave going down, and then the wave coming back up is slower, that maybe it just nets out if you got the same ejection rate. So I have tried both of them, and they did seem to come out pretty similarly. I had I didn't have any downhole markers though, so I was basically having to copy the same acoustic velocity, you know, looking at tubing collars when it was shut in, because there's so much noise when it's injecting gas. But
you know, you're kind of getting to kind of like an Einstein question here, is theory of relativity, but I don't really know the answer. But
that's fair enough. Maybe you can tell me another answer. Looking at you evaluating collars on this screen you have up here, right here, I always use the BP filter, the bandpass, and here you are using the HP.
I've gone up to a higher interval, and the high frequency signal shows the collars better, and I can see each of the kicks. So
when you go lower though, take it lower and then try the bandpass. It just seems I almost always use bandpass. Go lower where you were. You were down there at like 4,000 something feet. Oh, not that low.
No, just a minute now. I'm going to show you what you're asking. All right. So if I come in here and I turn on the bandpass, ooh, those are good collars. Ooh, I like those. I can count those. I can count those. I can count those. I can count. So the problem I have with the bandpass filter, and I don't know if anybody agrees with me, but it always draws nice rounded collars, and you can always pick them. But if I turn on the high pass filter, I want to look for kicks. There's a kick. I want to find the kicks that look like collars and count those. And so I prefer using the high pass filter because I can see the color echoes, and the bandpass filter has a band, a color frequency range that makes a wave that looks like collars that you can count, because it's a narrow range. And so I usually don't use the bandpass filter, but it's typically what we'd see if we use a strip chart and use the lower collar filter. So the well signal naturally degrades into a nice sine wave in a well at depths more than about 3,000 or 4,000 feet, and the collars tend to disappear and make a wave. So bandpass filter theoretically should emphasize the natural frequency of the well deep in the well. The high bandpass filter, typically when casing is large diameter, you get a lot more noise on the between the collar echoes, and so usually I'll turn the high bandpass filter on when it's 7-inch or larger casing.
Okay.
Okay, we have.
I appreciate it.
Thanks, Joe. We have a couple of more questions. Lynn, before probably you want to show an example, but this might be quick answers. Well, one question is from Hindi and Tunisia asking, for the implosion mode, is a static pressure in the chamber needed to minimize the differential?
Yes. Normally we don't really recommend putting more than 1,000 pounds differential pressure to make a shot. We don't use more than 1,000 pounds differential pressure for the very high pressure gas gun, and that's not bad practice to carry down to the 5,000 psi gas gun, even the compact gas gun, because more pressure means a bigger shot, but more pressure is more energy, and it could cause some kind of a problem, more wear with the O-ring, more potential for something not to work quite right. So usually you reduce your noise at the beginning of the shot by reducing your differential pressure. So the rule of like 300 to 400 or 500 pounds of pressure still applies when you're doing an implosion shot. You can control the differential pressure by not bleeding all the pressure off inside the gas gun. So an answer is sure, you should control your implosion differential pressure just like you'd control your explosion differential pressure.
Okay, thanks. And we have the last question, at least so far, asking how much the maximum casing pressure is available to shoot an echometer. As an example, if the casing pressure is 1,000 psi.
Okay. So if I have if I have a gas gun, the gas gun type of gun is going to determine how you shoot this well with 1,000 pounds of pressure. So normally when you have 1,000 pounds of pressure, if you have a remote fire gas gun, that means you're going to have to charge your gas gun with nitrogen pressure and do an explosion shot. The remote fire gas gun mechanism inside the gun doesn't allow it to do an implosion shot. So you're somewhat restricted, and the working pressure of the remote fire gas gun goes up to 1,500 psi pressure. So that's going to be the maximum pressure that you could typically charge your gas gun to and be within the working pressure of the gas gun. Now if you have a compact gas gun, you could do an implosion shot or an explosion shot because it's not unusual to have nitrogen gas to charge a compact gas gun to a pressure of more than 1,000 pounds of pressure. But probably we'd do an implosion shot. It's going to blow some debris into the gas gun and potentially make us take the gun apart and replace an O-ring because it might get cut with some sand. So, maybe your preference in a well that that has debris in the well is to do an explosion shot, even though the compact gas gun could do an implosion shot, because you don't really want to have to do maintenance on your gas gun. You could clean the wellhead and do an implosion shot. If you have the higher pressure gas guns, the 5,000 and 15,000 psi, they would work just fine with 1,000 pounds differential pressure. But maybe you would put less pressure in the gun differential pressure because the fluid level is close to the surface. So that would be my answer. I mean,
Okay. Well, linking the next question with the implosions, what is the minimum casing pressure required for an implosion shot?
There's not really a minimum pressure because the gun has to open to make an implosion shot. So as long as you can open the gun and the pressure on the outside of the gun in the well is higher than the pressure on the inside, it'll create a traveling wave. So I don't really see there's a limit, but if the well is shallow, we may want to do a tiny implosion shot. If the fluid level is high, we may want to do a tiny fluid level shot. There's the well we teach the class at, which is south of Wichita Falls, about 4 miles, the V11 well. We often demo the different gas guns on that well and the casing pressure on that well is usually about 85 psi. And Ken Skinner frequently shoots the fluid level with the 5,000-pound gas gun, and you can, in a 5,000-foot deep well, you can see the lick level echo. So there's not 85 psi is probably a low pressure for an implosion shot. And then if you read the manual, it will say if you have 200 pounds of pressure, you can do an implosion shot. So there's not really a physical limit, but to get good quality echo, probably 200 psi or higher differential pressure would be the normal amount of pressure for an implosion shot.
Yeah, thanks. Keeping clear that they have shallow wells. Sometimes only 50 psi is enough.
Yeah.
Shallow fire wells, yes.
Yeah, less could be.
Okay.
Yeah.
We have one more question from Andres Solano. He's asking, it's related to the gas gravity calculation from the software compared to a gas chromatography. So it says, has the specific gravity value being compared against some gas chromatography?
Yes.
He read the paper, and he would like to know more about it and how accurate is that value.
Okay, so about 25 years ago, I did something like that. We shot fluid levels on 55 different wells, and we took gas samples on the casing gas. So you have to specifically sample the casing gas if you're going to shoot the fluid level and not use the gas from the plant or the gas from the separator. We did that. And as long as the percent CO2 was less than about 30% CO2, then the hydrocarbon gases, gas gravities, it might be a 0.83, and the gas analysis would be like a 0.81. Usually within 2%. 2% or so was a typical error when the CO2 percent is less than 30%, because the acoustic velocity is a measured value. We have a correlating algorithm inside the software that calculates the relationship. So I guess that's my answer. It's very accurate. Once you get more and more CO2 in the gas, then the CO2 gas doesn't act like a hydrocarbon gas, and so it doesn't. It's not as close. So there's more and more difference between the gas gravity from the software when you compare it to gas composition. I'd say more than 30%. Now, one of the things that we've done inside the TAM software, if you put 100% nitrogen for the component, then we put in the PVT properties of nitrogen, and we calculate up to very high pressures the gas compressibility and acoustic velocity and pressure gradients for pure nitrogen. So if you have a gas that's primarily the nitrogen, and you say it's 100% CO2, then the properties we're going to calculate based on the nitrogen percentage will be very, very accurate. So we use the National Institute of Testing and Standards to come up with that those correlations. So that.
I have one more question,
Okay.
and it's related to from MPR. He's asking, if a well has a high GOR and there is a foam column present, is there any possible signatures I can look for to determine the actual liquid level depth?
Okay, that's an interesting question. So when you have a high gassy fluid column, the gas is flowing through the fluid, then the gas is typically flowing at the same rate from the bottom of the fluid column up to the surface of the fluid column, and the gradient has been shown to be constant versus depth. And so back in the 1980s, Echometer developed the papers on our webpage, Echometer gaseous correction factor curve for producing fluid levels on producing oil and gas wells. And that takes the percent liquid and is calculated. The percent liquid is calculated from the annular gas flow rate. So that's the technique that we use, and it can be very accurate. So that's a feature that's currently done now. If you want to determine the gradient of the fluid in the annulus, since it's a gassy well, then back in the 1930s, a developer of acoustics theory named Walker, C.P. Walker, developed the Walker fluid level depression test. And that test has been around for a long time. And the way that works is that you put a back pressure valve on the, say you want to do a test of the gradient on the casing annulus, and you put a back pressure valve on it and stabilize the pressure at the surface, and you shoot fluid levels for a period of time, and then you increase the pressure and shoot fluid levels, and increase pressure and shoot fluid levels, increase pressure and shoot fluid levels. And what you find is if you plot the height of the gassy fluid level with the stabilized height of the gassy fluid column, so you plot the height versus the pressure at the top of the gassy fluid column, then that plot is a straight line, and that represents the change in pressure versus change in height. And PSI, or pressure change versus height change, is a gradient, and you actually can measure the gradient doing this Walker fluid level depression test. So, if you're interested in more about the Walker fluid level depression test, you should email one of us, and we can send you more information about that. But that test has been around for a long time. The information that we collected back in the 80s is inside the Echometer software. We did another series of tests in Venezuela for viscous crude, and we automatically calculate the gradient of the gassy fluid column based on the pressure buildup and the fluid level shot. So that's a standard calculation we do. Okay, so what I have now is I've got, looks like about another 30 minutes to go, 20 minutes to go before 4 o'clock. I've put in the presentation at the each page or each slide, I put a name of the well with the folder, and so you'll be able, and not now, but soon, you'll be able to go to our web page and download this TAM data file with all these examples in it, and you'll be able to match the PDF presentation slide with an example well and look at the data with the TAM software. So let me show you the TAM software here. So when I click on pick a well on my computer, here is the downhole marker folder, and there's 14 different examples there that go along with this presentation. The one I have open right now is the fluid level from the Rotoflex well. This data was used to compare and show the downhole marker method compared to the automatic method. And so when you count collars, the software puts a line with the label C on it, and that represents how far the collars were automatically counted. And then if you use the downhole marker method, and like the tubing anchor, or a perforation, then you can use the known depth to determine the known depth to the liquid level. Often when we look at this acoustic trace, people ask, what's this noise here? And if you look, the noise is about 8 seconds apart, and that's the time for half of a stroke. And so this noise here and that noise here is the weight box inside the tower of the Rotoflex unit, banging on the pump unit, making noise on the acoustic trace. And if we go in and apply the low pass filter, then that noise disappears. And so this is a common question. We've already talked about the markers, and we've talked about the collar count. So I'm gonna go to a different well unless someone has a specific question on this well. So let's pick a well. The hole in the tubing, there's a hole here in the tubing here on a gas well, and there is a tubing hole here on a rod pumped well, and this well right here, this BKU 55, is a well that goes along with that technical paper. So I'm going to pick this well first, and then we'll look at a couple other wells that have holes. So let's look at this well first. This is a well out in West Texas. This paper was published in 2014 at the Southwest Petroleum Short Course. It's a rod pumped well. This is the surface and the pump card. Up here is the fluid level shot. So if I click on that button, it opens up the acoustic trace. This shot was acquired on February the 11th, 2014. So it's fairly old acoustic traces, but they still are the same. if you look, there's a comment here that's talked about what the operator did when they acquired their data. The test that we want to look at is this test right here. And this test, if you look at this acoustic trace, you can see the Wellbore overlay in the background. Now the Wellbore overlay, if you go to annotations, you can make it darker. It's selected. You turn it off or on, and you can make it darker or lighter. So we usually leave it somewhere in the middle here, so you can still see the acoustic trace and the Wellbore. So you can see the tubing anchor marked on here, and you can see perforation marked. It's probably a top perf here that we see this upkick right there. I don't see it. I don't see a perf mark. So if we go, but that's probably a top perf, that sharp upkick. The depth was done by counting collars, and the collar count line was down to here. But you can see that the tubing anchor down kick, it doesn't line up with the anchor. So if I was going to analyze this shot right here, I look at it and I'd say the tubing anchor needs to line up with the anchor marker. So I'd go into down on marker method, and I'd pick the tubing anchor. I'm going to scale this down a little bit. I'm scaling it down, and I'm going to move the anchor marker to right there on the down kick, and I can fine tune it down here at the bottom right to the knee of the kick. Okay, so there's our marker that's used to determine distance to liquid, and the liquid level is either here or right below that, probably the top perf. I'd probably pick the liquid level at that point right there. So if I was going to analyze this well, I'd probably move the liquid level to that point, to that kick right there. So that would be my analysis, and I go back and look at the well file, which I may or may not have, and I'd probably put in the top perf and verify there's a top perf right there. There probably is a top perf right there. So why was this one selected as an example? Because this is a test on 1/6/2014. Well, prior to that, this well had a hole, and the hole was discovered on 2013, and this is the down tubing shot, and this one is the casing shot. So here's the casing shot here, and the liquid level is down here, and looks like we put the liquid level at the hole. Okay, so that's where the hole's at. But so how can you tell there's a hole there? You can't tell by looking at this trace that there's a hole. If you scale it down, it's still not obvious there's a hole right there. But if you turn on the low pass filter, apply low pass filter, then you can see the upkick, and you can see the repeat down kick. That is the repeat of the inverted, well, you send a down kick down the well, kicks as an up kick at the hole, the up kick goes back to the surface and repeats as a down kick. It gets inverted by the hole, so it's a down, up, down. So that's the depth of the hole shot down the tubing, no, down the casing, with the low pass filter displayed, and we put the liquid level marker there to get the depth. We could have, if we didn't want to put the liquid level marker there, we could have put the liquid level marker in the correct place and gone to annotations and turned on the depth reference line and pulled the depth reference line up to that same point. So there would be the correct, probably the more correct method to pick the distance to the hole. Now if we go to the tubing shot, which is right here, and we look at it, you can't see much of anything because again you're overlaying signal with high frequency noise on top of the casing filtered signal, and they're laid on top of each other, and so they're difficult to see because we're looking at the entire trace. But if we take this dot right here and move it to the left and expand the scale on the screen to a point where it's all stretched out, we can see this upkick from the, let me turn this off just for a second. Go into annotations and a previous shot and turn off this previous shot here. And so now here's our all right. So here's our shot down the tubing, and these are the echoes off the rod couplings, and these are 25-foot spacing, and there's the upkick, the hole in the tubing from inside the tubing on our suck rod well, and the liquid well is right below that upkick. Now we don't need to filter it, but we could filter it. If we filter it, then all the collars, the coupling echoes are going to go away. So we're going to leave the filter on. And if you want to overlay these two kicks, you go into annotations, a previous shot, and select the previous shot right here, and that'll put the, if I can scale this up a little bit here. See, there's the upkick right there from the casing shot, and there's the upkick from the tubing shot. And this is saying the acoustic velocity is 963, which is not the same acoustic velocity here as, well, let's count collars. Count the collars, scale it down. All right, so here's the collar count. The collars are easy to see on the casing shot. Now you can see them pretty well. So those are the tubing collars on outside the tubing. We get an acoustic velocity of around 1142, and there's our upkick. And if we go back in to analyze the tubing shot, then we'll need to put the same acoustic velocity to make this kick and that kick line up, which was 1142. And now the two kicks line up because they have the same acoustic velocity. All right, so that's an example of getting these two to overlay. They overlay now with the same acoustic velocity. They match up. Any questions about this? Let me show you one more example real quick. We're looking at this screen right here. I'm going to turn off the previous shot, and I want to demonstrate the overlay. So this kick right here, there's being a shot. If you fold the trace in half at the, let's say at the up kick, then this kick and that kick's going to match this kick there, and that kick will match up. So go into annotations, fold the trace, and if we're right there at that kick, then the beginning of the shot and the up kick right there, they match up. So that's I guess it's a down kick from the repeat of the hole. But the fold the trace will let you fold the trace and see if the kicks, when they are folded, the beginning of the shot and the repeat echo match up at the beginning of the shot. So that shows they match up. All right, so that's kind of the end of the presentation. I hope you all enjoyed it. Carrie Ann, do you have some final words to say?
Yes, if you do have any follow-up questions, we of course welcome phone calls and emails. We have a recorded video of this session that we will put on our website tomorrow. And along with it, I'll have a folder where you can download a PDF of the presentation. I've made a list of the papers that Lynn referenced during his talk and in answering some questions, so I'll make sure and cite those, along with all of the example data that he's used during the presentation and then his follow-up examples too. So next week's session is going to be over dynamometer analysis. Lynn's going to show examples of unaccounted mechanical friction forces and how they affect downhole pump carts. The title of the presentation is Examples of Forces Not Accounted For by the Wave Equation. And so we hope you guys will join us for that. If I have your email address, if you've registered, then I'll automatically send you a link. And if you're joining us and you haven't registered or sent your email in, I can put my email address out here so that you can get in contact with us. But we sure appreciate your time and certainly look forward to seeing you all again.
I hope you all enjoyed the presentation and answering questions. All right, well that's it for me.
All right. Thanks, everybody.